Good morning. This presentation is titled Algorithm-Based Checkpoint Recovery for the Conjugate Gradient Method. It is work by Cristina Paja, Markus Leboniek, Wilfried Gansterer, and myself, Carlos Pachacoa. This work was funded by the Vienna Science and Technology Fund, and we use the VSE3 machine of the Vienna Scientific Cluster for our experiments. In the motivation for this work, we have two aspects. The first one is the unreliability of computer systems in the large scale. We usually think of computers as reliable machines, in the sense that they will not produce errors spontaneously. But in reality, they do, although the likelihood of an error happening in a PC or a computer node in a window of time is very small. However, the most powerful machines today are not single-node machines, but rather clusters of interconnected nodes. And of course, the more elements that are working together in a computer, the more likely it is that an error will happen in a window of time. That is, that the mean time between failures decreases. It is expected that for exascale machines and larger, with hundreds of thousands or millions of nodes, this is going to be a considerable problem. And coming up with solutions for this is an important research question. In this work, we focus on a category of faults called node failures. These are events in which a node or several nodes stop working, and the data contained in them is lost. If it's not only the node that fails, but if a switch goes down, then we effectively have the simultaneous failure of several nodes. The second aspect in the motivation is the use of the conjugate gradient method. This is an algorithm for the solution of linear systems of equations, defined by a symmetric positive definite matrix. These matrices are very important in areas of science and engineering, and therefore it is worth to invest looking for strategies to keep these linear solvers resilient and reliable, in particular when dealing with very large systems that are more likely to encounter a node failure event in their lifetime. We come to the problem statement. We are working with an unreliable computer cluster that can suffer node failures. We are looking for the solution of a linear system defined by a symmetric positive definite matrix, and we are using the conjugate gradient method. We assume that the matrices are stored in the block row distribution among the cluster nodes, and that the vector entries are distributed in the same way the matrix rows are. I'm going to introduce the techniques and algorithms that we use in this paper with three key ideas. The first of these ideas is that we can use the matrix vector product to obtain some redundancy in the input vector. This idea was first introduced by Chen in 2011. This is an example to illustrate how the process works. This is a sparse matrix where the dots represent non-zero entries being multiplied with the dense vector to the right. The matrix is distributed among four nodes, 0, 1, 2, and 3. And we will focus on what happens with the output vector in the indices of node 1, highlighted here in blue. Each node computes a partial matrix vector product by sharing the input vector entries such that each of the nodes has enough information to find its portion of the output vector. We can mark with vertical lines what parts of the matrix will operate on parts of the vector that have to be communicated from other nodes. And since entries of the vector are being communicated from their owner to other nodes that need them for the product, then we do have some redundancy in the entries of the vector since they exist simultaneously in several nodes. Therefore, all we have to do is keep them to maintain the redundancy in the data. Now we're going to see what happens to entries corresponding to node 1. We're going to hide some blocks of the matrix and leave only the blocks that are relevant for determining where these entries have to be sent to. That is, what nodes will be receiving entries owned by node 1. We take a look at the first entry of node 1 and see that it's being sent to node 0 and node 3 during the matrix vector product. So it's being held by two other nodes. Then the third entry is sent to node 2 and node 3, and the fourth entry is sent to node 0. All of this is determined by the sparsity structure of the matrix. These three entries have redundancy stemming from the matrix vector product itself. But what happens to the second entry? It's not sent at any point during the matrix vector product. In the event of a node failure, this entry will be lost, and in order to conserve it, we have to augment the matrix vector product to make sure that this entry is also sent to some other node, such that it is redundantly stored. We call this operation the Augmented Sparse Matrix Vector Product, ASPMV. Of course, this additional redundancy doesn't come for free. You have to pay for the communication of sending additional data that is not necessary for the product. And in fact, this paper deals with reducing the impact of this overhead. These ideas can also be generalized to the simultaneous failure of several nodes. And in order to do that, we introduce the concept of multiplicity of an entry, which is the number of nodes that an entry is sent to. In our example, the first entry has a multiplicity of 2. The second entry has a multiplicity of 0 because it's not sent to any other node, and the third and fourth entries have multiplicities of 2 and 1. We want to increase the multiplicity for each entry up to at least the number of redundant copies that we want to have. So, if the matrix vector product is conducted in such a way that every element has a multiplicity of at least phi, then after the product we have phi plus 1 instances of the value of the element, the phi copies plus the original element. Therefore, if up to phi nodes fail, there will be at least one remaining entry that we can use to reconstruct the vector. This augmented sparse matrix vector product gives us a tool to store a vector redundantly. Now we come back to the conjugate gradient method. The algorithm involves a matrix vector product with the search direction p. Therefore, this vector can be stored redundantly and it can be retrieved after a node failure. The algorithm is shown to the left and the matrix vector product is highlighted. To the right, we have the exact state reconstruction algorithm, ESR, that reconstructs the entirety of the state of the conjugate gradient solver after a node failure. For the reconstruction, we need to retrieve the static data, like the matrix, the preconditioner, and the right-hand side, gather the residual and iterant vectors, and retrieve redundant copies of the scalar beta and the last two search directions that we store redundantly. Then, in line 4, we see that with these last two search directions, we can compute the preconditioned residual set, and with set, we can, in line 6, recover the residual. And with the residual, we can reconstruct the iterant itself. So, what we're doing is constantly storing copies of the search direction such that we can reconstruct the state at any time. Now, keeping these redundant copies causes an overhead. And the main question of this work is, what happens if we try storing redundant information not every iteration, but every t iterations? This is our third key idea. Here we have a simple representation of the conjugate gradient solver going through its iterations. Now, let's say that we want to store redundantly every 3 iterations. So here they are marked with red circles. This means we only use the augmented sparse matrix vector product in these iterations, and for the rest we use the regular product. There are 2 problems with this. The first one is that if we take a look at line 6 and 8 of the ESR algorithm to the right, it doesn't produce a consistent state by itself. It just produces the pieces of the vectors that were lost during the node failure. For example, suppose that at iteration j plus 3, we store the redundant information for the search direction p. Then, in iteration j plus 5, we suffer a node failure. If we try to reconstruct using this information, we will end up with the information corresponding to iteration j plus 3 in the positions for the lost nodes. But the rest of the vector entries have changed and contain the entries corresponding to iteration j plus 5. So it is not consistent and cannot be used. The solution to this problem is to have each node back up its entries of the vectors for that iteration. This is not a large overhead. The cost is just the memory to store the vectors and performing a local vector copy. It is important to notice that if a node failure happens, these local copies cannot be used to reconstruct the state of the solver. The second problem is that we need 2 consecutive search directions so that we can perform the reconstruction. And because of this, we have to introduce a queue to redundantly store data. We'll take a look at what this means right now. We are going to see what happens when we iterate and we want to store redundant information only every t iterations. From the start and until iteration t, in the event of a node failure, we will have to revert to the start of the solution process. In all of these iterations, we proceed with a regular sparse matrix vector product. Then, in iteration t, we push the first redundant copy of the search direction, and in iteration t+1, we start the second one. With these two consecutive search directions, we can reconstruct the state of the solver. We continue iterating, and from here until iteration 2t, a node failure will send us back to iteration t+1. We continue, and once we reach this iteration, we push again. But we still don't have two consecutive search directions at this point. We only have the old ones. So if something happens at this point, we still have to revert all the way back one period. But then, after one additional iteration, we have two consecutive search directions and we can reconstruct here. And in the event of a node failure happening from here to the next period, then we revert to iteration 2t+1. For the description of the algorithm, we introduce two functions more formally. The first one is the regular sparse matrix vector product, ASPMV, which takes the matrix and the input vector as inputs and produces their product as output. The second one is the Augmented SpMV. It takes the matrix and the vector, but additionally it takes the target number of redundant copies, the minimum multiplicity, and the Q for the redundant copies. Here we have the regular conjugate gradient method that we use for comparison. And now, to the right, the conjugate gradient method with periodic storage, which we call CG-ESRP. We can see the changes that we require. We store two consecutive items. We are storing into a queue, and additionally in lines 9 and 10, we are saving the solver's vectors and scalars in order to be able to reconstruct the state later. Now we come to our experimental results. First, we are going to show our setup. We are using the VSC3 machine of the Vienna Scientific Cluster, and we use two strategies. The first one is ESRP, and the second one is in-memory checkpoint restart, or IMCR for short. The latter is a checkpoint restart approach, meaning that nodes will store all of their contents in some other node in the cluster. The difference between IMCR and ESRP is that IMCR stores all of its information, whereas ESRP just sends some additional information during the matrix vector product. We are simulating node failures, and we are using checkpointing intervals of 20, 50, and 100 iterations, both for ESRP and IMCR. We simulate simultaneous failures of 1, 3, and 8 nodes, and we are running experiments without resilience, with resilience but without node failures, and also with node failures. These are the test problems that we are using. They come from the Suit Sparse Matrix collection, and they are Emilia 923 and Audi KW1. These are middle-sized problems. Finally, we have some plots for the results for matrix Emilia 923. Here, we define the reference time as the median runtime for a regular solver without any resilience. We are showing the overheads with respect to the reference runtime for this matrix. This plot presents the results without node failures, so they only represent the overhead of maintaining the redundant copies. The green line represents the ESR approach, which is the same as ESRP with t equal to 1, and it's shown here only for reference. This line is the same for all checkpointing intervals. Every line connects 3 points, and these are cases with 1, 3, or 8 redundant copies from left to right. The most important message from this slide is that increasing the checkpointing interval for ESRP can drastically reduce the overhead from maintaining these copies, especially in the case with 8 redundant copies, where this cost goes from 9.1% to 1.1% in the case of t equals 100. We see the advantage of ESRP both compared to ESR and to IMCR. To the right, we introduce node failures. As many node failures as the solver can tolerate, again with 1, 3, or 8 copies in each line. In this case, IMCR is faster than ESRP. Here we can also see that ESRP is in general faster than ESR, especially for situations where a larger number of nodes fail simultaneously. These plots also show something that at first glance would look like inconsistencies. In the failure-free case to the left, for 1 and 3 redundant copies, the overhead is smaller for a checkpointing interval of 20 than it is for 50, which is not what we would expect. With introduced node failures, in the plot to the right, we also see that there are cases where ESR is faster than ESRP. To explain this, we can take a look at the standard deviation of the reference time, which in this case is 0.93% of T0, the reference time. If the runtime differences are so small that they are close or below this value, they might be overshadowed by the variation caused by the machine. These are the same plots for the matrix Audi KW1. This is a failure-free situation. We also see a dramatic reduction for the overhead of ESRP when we increase the checkpointing interval, going from 7.4% for 8 redundant copies to 0.4% for an interval of 100 iterations. Now, the advantage of ESRP over IMCR is not so large. The methods remain comparable in the failure-free case, but ESRP is faster if more nodes fail simultaneously. Also, in this case, ESRP is much faster than plain ESR. To the right, we have the plot with introduced node failures. In this case, IMCR is faster than ESRP. We found out that most of the cost of the reconstruction in the event of a node failure for ESRP comes from solving a local linear system during the reconstruction. In IMCR, of course, this operation is not necessary. You just have to copy the information back to the owner node. Going back to the failure-free case to the left, we can see that IMCR is comparable to ESRP, even though the amount of information that IMCR has to send is larger. And this makes us believe that our examples are just too small to actually go to regimes where communication dominates the cost of the operations, which is expected to be the case in very large machines. We conclude that these results might not reflect every advantage that ESRP might have over IMCR in very large problems running in large-scale machines by virtue of communicating less information. Now we come to our conclusions and perspectives. We have seen that in our first experiments, the exact state reconstruction algorithm with periodic storage drastically reduces the overhead over the regular ESR algorithm. Also that in cases without node failures, ESRP is usually faster than in-memory checkpoint restart, particularly for cases where more nodes fail simultaneously. In our experiments, the cost of communication seems to be too low. IMCR, which transfers much more information than ESRP, incurs in almost no overhead for this communication. We cannot conclude that IMCR is faster than ESRP, and experiments at larger scales are required. We have observed that the recovery time for ESRP is dominated by the solution of the local linear system during the reconstruction. This is therefore a critical aspect to investigate in this area. In perspectives, we intend to perform experiments with larger problems and with a larger number of nodes, such that we can reach a different regime in the computation to communication ratio, and we can observe a more realistic situation. Also, following a suggestion of one of our reviewers, we would like to develop algorithms that are aware of any matrix partitioning method used to pre-process the matrix for the solution of the system. Finally, we want to produce an implementation of these algorithms that can deal with real node failures, using something like MPI ULFM to deal with them. This concludes the presentation. Thank you very much for your attention.